Now we're going to talk about the error that occurs in the accumulating sum for an alternating series. Now, the one thing that I want to set up a baseline for here, so we understand this is what's going on. Here I'm going to call this b sub n because they have the terms here as b sub 1, b sub 2, b sub 3, and so on. And you can see b sub 1 is a positive value, b sub 2 is a negative value, and they alternate, and so forth. And here is the actual sum. The actual sum is accumulating to S. So S is the actual sum with infinitely many terms. That's the total sum with all the terms added together. Now, the one baseline that I want us to understand is that we are talking about a convergent series. And we talked about the fact that the last term in the series had to be bigger than the next term in the series for an alternating series. And that is the case here. And we can see if we follow the work that they've done, they start at 0, there is no sum, and then the first partial sum, S sub 1, contains the first term, b sub 1. So it's a distance of b sub 1 from 0. Then from S sub 1, they come back, because b sub 2 is a negative value, the value of b sub 2, and that gets us to our second partial sum, which is b sub 1 minus b sub 2. So can you see what they're doing here? And from that second partial sum, b sub 3 is a positive value. So they come over here to the third partial sum. Sorry, that should be a 2. The third partial sum is b sub 1 minus b sub 2 plus b sub 3. So hopefully you can see what's happening here. We go back to the fourth partial sum, back in the positive direction to the fifth partial sum, back in the negative direction, and so forth. And you can see all these little tick marks here. We are converging. This is a convergent alternating series. Whose sum is S. So make sure all that's in your notes. I want to do all that as kind of a background to what we're fixing to talk about. So if we use any nth partial sum to approximate the actual sum, it becomes important for us to know what's the difference between those two. What's the difference between the actual sum and any nth partial sum? That's the question we're going to ask ourselves, because this is the error bound. That is the biggest the difference or the error in our nth partial sum and the actual sum could be. So we don't care if it is an over approximation or an under approximation. We don't care if our nth partial sum is bigger than the actual sum or if our nth partial sum is smaller than the actual sum. What we're after is the difference. Whether an over approximation or an under approximation, our error bound is the difference. Let's put this in your notes too. If I can get things to work out here for me, please. There we go. The error bound is the difference between the actual sum, we call S, and any partial sum. we're calling S sub n. So let's go back and look at what they have set up here for us. And let's see if we can determine what the difference could be. So what is the difference? Let's see if we can figure this out. What is the difference between the second partial sum and the first partial sum? What is that difference? Well, we said the first partial sum was b sub 1. We said the second partial sum was b sub 1 minus b sub 2. So if we have the second partial sum, b sub 1 minus b sub 2, and we're subtracting from that the first partial sum, which is b sub 1, then the most the error could be would be b sub 2. That next term is the most that the error could be between those two. And if you'll see here, for any partial sum, the biggest that the error can be is just the next term. We're guaranteed, because we're closing in on the actual sum from one side and the other, because this kind of idea is going on, we're guaranteed that the error must be less than the next term in the series. The actual sum itself must lie within that interval. And if you'll look at every one of these intervals, the actual sum itself does lie within that interval. That is the absolute max that the error can be. So that's what this means. This says the difference between the actual sum. Now, understand, the actual sum has infinitely many terms added together. That's an infinite series. So the difference between the actual sum and any partial sum, we call partial sums S sub n, has to be less than or, give myself some more room here, equal to the next term. And we just illustrated that right here when we did that. The actual sum will lie within that interval. So that's what this means. Here is the error bound for a convergent alternating series. So the error bound in a convergent alternating series is simply the next term. The difference between, I can promise you, the actual sum and the 100th partial sum must be less than the 101st term. That's what this is saying. The most the error could ever be is the value, whether over or under, that's why we're using absolute value, of the next term in the series. And that's why I chose to use this picture, because I think it does a great job illustrating why that has to be true. There's a lot of theory behind this, but I don't have time, nor am I going to go into all the theory. So let's get down to putting that into practice. So this says show that this alternating series converges. Well, first of all, I need to find the nth term. Your nth term doesn't have to look exactly like my nth term. You may choose to put n minus 1 up there. I choose to put n plus 1. That doesn't make me right and you wrong, or you right and me wrong. As long as we generate the same series, then it doesn't matter. But there's the nth term of this series. It's clearly some alternating term times 1 over n factorial, where n starts at 1. So I'm going to run the alternating series test. And there it is. The bigger n gets, the bigger that denominator gets. 1 over huge is tiny. That limit is going to 0. This series converges by the alternating series test. So after the last lesson, that's not an issue for us. We can find where these alternating series converge or diverge. We could even talk to them about conditional and absolute convergence. The next thing says calculate S sub 5. S sub 5 is the sum of the first 5 terms in the series. That's what S sub 5 means. So the first term is 1 over 1 factorial. Second term is 1 over 2 factorial. But it's a minus. I've got to watch this as an alternating series. Careful. Minus 1 over 2 factorial plus 1 over 3 factorial minus the fourth term, 1 over 4 factorial, and plus the fifth term. So that's actually a number. We could actually walk away from that, but I want you to kind of sort of see if you did have to pick this value up and do anything with it. It might take you a little time, but you could find one fractional value for that. But we don't have to simplify, so we don't have to worry about it. That is the fifth partial sum for this convergent alternating series. Now the next question says calculate the error bound using S sub 5 to approximate S. Now I know that I will have to know, you will have to know, in other words, how to put that together in symbols. So the error bound using the fifth partial sum to approximate the actual sum must be less than the next term in the series. So the error bound, and again, we don't care if it is an over approximation or an under approximation. It's actually a negative term, and it's 1 over 6 factorial. We usually don't bother to write that negative in there because we are just concerned with whether it's, its absolute value, the magnitude of the difference between the fifth partial sum and the actual sum. So let's look at one more example really quickly. I think we can get through this before the end of the video. So find the sum of the series correct to 3 decimal places. 3 decimal places. 3 decimal place accuracy. Well, we could generate some terms, which I've done here. I've generated the first 7 terms. And then I have put them in their fractional values. And I'm looking for a term that is going to guarantee me 3 decimal place accuracy. And that is the first term that guarantees me 3 decimal place accuracy. So in other words, the difference between the actual sum and the 6th partial sum, which must be less than the 7th term, will give me an error that is within the acceptable bound. So that's not difficult either. You just have to generate some terms, see how many terms you need to come up with, and that's all there is to it. So come to class next time and we'll work on alternating series error bound.